Hey, what's up, guys? This is Cheng here again. So this time, LeetCode number 1915, number of wonderful substrings. Okay, so a wonderful string is a string where at most one letter appears an odd number of times. Okay, so this one is another like problem that you need to uh, work with the parity, right? A parity of the occurrence of some letters. And this one is like it's a little different constraints here. So for example, we have this string here and this one, and they are wonderful because in this string, so C a letter C has an odd number of times, right? Appears odd number of times, and J appears even number of times. So which is fine. And this one AB is also fine because in this one both A and B appears. Basically, there's no letter that appears at odd number of times, but AB is not because both A and B appears an odd number of times. Okay, and then you're given like a string word that consists of the first 10 lowercase English letters, right? So this and return the number of wonderful non-empty substrings in the word. Okay, and then if the same substring appears multiple times in word, then count each occurrence separately. Basically, if you have duplicated same string appeared multiple times, so each one of them should be counted to the final answer, right? So for example, we have ABA, right? So this one, the answer is 4 because obviously, the letter itself is a valid. One single letter is always a wonderful string here, right? That's why we have ABA, and then in total, ABA is also a wonderful substring, right? Because this one only B appears odd number of times, and then we have another one AABB. The answer is 9, right? So this one like it's H and E because the letter itself is always the answer, right? The one of the answer, and then constraints 10 to the power of 5, and this one, right? So look at this. So the only 10 letters in total. Okay. Yeah. So for this one, actually, a brute force way is obviously just trying to do like find all the substrings, right? And then you'll basically find then for each substring you check if that substring is a wonderful string or not. But that will definitely tell you because just to find all the substring you need n squared time complexity, right? Okay, so for this kind of problem, and this one is a count, right? So for this kind of problem, you either use like a DP to solve it, right? Or yeah, actually, most of this kind of string counting problems are will be solved by using the DP concept here. And for this one, the tricky part is that how can you efficiently check, right? At the current state, at the current index, how can you efficiently check what are the wonderful strings? I mean, so far, right? That's why we need to use this kind of like the English 10 letters, right? A and J. So we have to use this one. Otherwise, it doesn't make sense to give us this one, right? I mean, this one actually is very similar with one of the problem we just talked about like a while ago. And for that problem, I believe that problem is to find the longest substring whose um, whose I think odd oval letters are even, right? If you guys remember that problem, I think 1044. That's a problem number. In that problem, we use a bit mask with 5 digits to represent the parity at each state, at basically for each of the prefix, right? And for this one, actually, we will be using the same concept here. So this one is also DP with a bit mask. So the reason being is that uh, so first, right? I mean, let's say we have this kind of like substring here, let's say at the current state, right? Remember, so we have a 10-bit mask, right? So we're going to be a 1 0, let's say 1 0 0 1 0 0. For example, this is the bit mask. I'm not writing all the digits here, but in reality, there should be like 10 digits here. Let's say, so the way we're maintaining this bit mask is that, whenever we have C numbers here, we revert this bit values from 1 to 0 or 0 by 1, which means that, at each bit values, it represents the parity for that letter. Because this one's going to be a AB. I think it's going to be like this. So AB, we're starting from here, A, B, C, D, E, F, G, H, something, right? So 0 means that, okay, at this location, for example, here, right? At here we have even number of A's, and 1 means that at this location, the prefix stop here has odd number of C's. And why do we need to maintain this one? Because so first, if we can find the same, same bit mask appeared before, then we know, okay, so basically two same bit mask, if we subtract that, let's say we have another one, let's say here, right? If this one has a bit mask, this one's also have bit mask, assuming they are the same. Okay, if they're the same, what does it mean? It means that, the substring in between, like this one, all the appearance, I mean, the appearance for all the letters, they must all be even, because the parity are the same, right? So odd subtract odd number of equals to even, right? And even subtract even also equals to even, right? So that's the first one. Basically, this one covers the one of the scenario. So the scenario that, since this one, for this problem, we are allowing at most one odd even letters. So this one, if we find the same like bit mask, then we have covered all the substring who have 0 odd appearance, right? Then how about the 1, at most 1, right? So for that one, actually, if we have the bit mask, right? So I think if you think about it a little bit more, right? So how can we find all the bit mask, even odd odd case with one letter? We can simply try to revert each bit value, right, one by one. For example, if we revert this 0 from 0 to 1, right, and we keep everything else the same, what does it mean? It means that, okay, all the other, if we can find such like bit mask before somewhere here, right, then it means that, okay, between that bit mask and this one, let's say this is a mask 1, right? So if we change this one, it means that this substring here, it means that, okay, this substring has a appears odd number of times, because all the others are the same. Only a is different. Then it means that and in this case, it means that basically the odd subtract even equals odd, right? And even subtract odd also equals to odd, right? That's how we use this one. If we revert one of the bit value, and then we can get this odd case here, right? And then, as you guys can see, we need to do this for each of the bit value, right? That's how we check all the possible scenarios, right? Who has only one letter appears with odd number of times, right? So that's that. And about the counting, right? So what if the since here we're only like checking the existence, but instead we should have like a dictionary to count the to store the appearances for each of the bit mask Because so the reason being is that let's say we have for example, we just use this the bit mask same mask as an example, which means that this even case here, it means that let's say this bit mask appeared 3 times in total. Okay, let's say this is the first time, right? That it appears the mask here, and then here it appears again, right? Okay, let me remove this one. So let's say here it appears again, mask here again, right? Same mask, and then in the end here we have another appearance here. Okay. Okay, so for example, we are at this like index here. Okay, so if we have 3 appearances of this one, right? So how many? If we have if at this one, so how many substrings, right? Basically ending with the current this I are wonderful strings. The answer is 2, right? So why 2? Because we have we have 2 masks that have the same mask with current one. So which means that so this is the first one, right? So this is the first substring. Basically, that substring is a wonderful one. I mean, in terms of the they're all even appearances, right? And the second one is this one, right? From here to here. See, that's the second one, ending with the current ladder here, right? So now, as you guys can see, so which means we need like a counter to keep track of the current the appearances, right? For each of the mask, right? And then at the current mask, right, we just use that to find the total substring by using the count of that mask. So either with the mask itself, or we try to flip each of the digits and try to find the odd even the odd appearance case. Yeah, I think that's it, right? I mean, once you figure that out, then the coding actually is pretty short, So we have a mask starting from 0, right? And then I have a count, I guess. I'll just call it count. It's gonna be a default dictionary, right? So the answer is 0, right? And then for C in Word, so we need to find the index, right? So the index is gonna be the word C minor. We're gonna convert this one to its integer value, and then we use this one to do some bit manipulation. So the mask is gonna be this one, right? Index, right? So this one basically every time when we see a numbers here, we find its corresponding index, and then we use this one to revert the bit value from either from 0 to 1 or from 1 to 0 by doing an XOR with this one, right? So this is like a small trick of how you can revert a bit value, okay? And then cool. So when we have this one, so the first one is this one, right? We're gonna count this one, the mask. So this is the scenario, right? So all letters appears an even number of times, right? So this is the even number case, and then for the odd number case, each letter, right? Basically one letter, right? One letter appears an odd number of times. So for this one, we have to basically check each number, right? So for I in range of 10, right? Because we have 10 letters in total. So the basically I'm using a pre-mask here. So pre-mask is gonna be the mask. This one dot, right? That's how we revert this flip the value of a bit, and then we're trying to check that, right? So this one's gonna be a count of pre-mask, right? And then in the end, don't forget to update the count for each mask, right? Cool. And then in the end, return the answer, right? So that's it. But there's like small things we have to be careful, which is the base case, which is the single letter case, right? So for the single letter case, so let's say for example, A itself should also be counted as 1. So if we're doing this, A will be 0 basically, right? Because for A, of course, the mask itself is empty. But if we flip A, right? So A is 1, right? If we flip 1 to 0, so we're expecting 1, right? But since the pre-mask will become to 0, and 0 does not have any values, that's why this one will be answer, which means for 0, right? Count 0, this one should be equals to 1. It means that the base case is 1 for all the single letter case. So which means if there's nothing here, right? That's how we can, for the single letter case, we can use this count pre-mask basically count 0 to give us 1, right? And that's it, right? So if I run the code, so it's not accepted, right? Yeah, cool. So that's it, right? Because this one it works because the time complexity, as you guys can see, is this one is n, right? So this one is n, and here, right? Here we're only having a 10 constant 10 loop here, which is 10n. Okay, and the space complexity, right? Space complexity. This one is so this is the time complexity, right? Time is this one, and space is what? Space is the this one, basically the 2 to the power of 10, right? That's the total possible number of the bit mask. Cool. Yeah, I think that's it, right, for this problem. Yeah, it's a very interesting problem. This is the second one that I have uploaded regarding the parity of the count for a letter, right? So for this kind of problem, just remember, I always use the bit mask. Okay, and to represent the odd and even, and we use the odd and even characteristics to find the even number of appearance of even number of times, or at most one odd number of times. Cool. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.